Oh, that's what I'm missing.
I was wondering, whatever I get wrong on the test, go over it somewhere, so I
Yeah,
understand what I missed.
yeah,
Yeah, that works.
yeah, we can chat after class, or, do you have a lab today?
No, I have it on Thursday.
Okay, well, you could always come during the Tuesday lab, and we
Okay.
could do stuff while other
Yeah.
people do stuff.
Okay. Yeah,
But-
that works fine.
Yeah, whatever works.
Very sick. With a new dog in the house.
Did you get them all stapled?
Yeah.
Awesome, thank you so much. All right, make sure you grab labs, so thank you, Trenton, for stapling them.
What's your name? I'm sorry. Ann? Yeah. You also, she also helps.
And helped as well, so thank y'all. And so make sure also, I got them on Thursday during your exam, so I like sporadically gave them to people, but make sure you grab an RCC science sticker, they're brand new, So they're up at the front, so grab one. You didn't get one on Thursday. And then I did grade the exams, so I'll hand them out during class or at the end of class. Overall, I was pretty pleased with the exams. People did well on them, so I think that's good. And I put in your extra credit, and we'll have other opportunities for extra credit as well. So I think that'll keep everyone's grades pretty high. So I'm not too concerned about anybody. And then I still owe you a lot of lab grading, so I'll work on that. I was focused on your midterms, so trying to get that done for you guys. All right, and then I just posted the live link today, so the notebook should be there now. And so we're starting chapter 17, which is chemical kinetics. And so we've kind of, talked about a lot of different things so far. We've talked about, like how chemicals react. We've looked at their states of matter. And so now we're going to look at the speed at which things react. And so that is chemical kinetics. How fast do things react, with what order? And so we'll look at what that means. And so our speed is called our reaction rate. And so the rate of the reaction is just a measurement of how fast the reaction makes products or uses reactants. And so this is really important. And so the big thing with chemical kinetics is we have to measure it. Right, so it's nothing we can guess about. We have to actually have an experiment, have some data, and be able to analyze that. And then we'll also, of course, see how we can maybe affect the rate of reaction. And so being able to control the speed of your reaction is important. So we've mentioned, the Haber-Bosch process, which is just how they make ammonia. So N2 plus H2 gives ammonia. Obviously not balanced, but this is one of those processes where chemical kinetics is really important. So being able to control this reaction, obviously the energetics of that, and then continue to drive that reaction forward. And so obviously, this is also important in industry and having good yields. And this also could go into a little bit of chemical engineering and how to engineer those reactions to be efficient. And so let's just talk in general then about factors that affect our reactant rate. So as you can imagine, concentration is going to have an effect. And again, as we might imagine, we can think back to our gas chapters, and more molecules, more collisions. And so anytime that we have more collisions, then of course we can have faster reactions. So greater concentration, more productive collisions, and faster the reaction goes. And so we see this in both concentrations of solutions and gases. And of course, gases, we've seen partial pressure, We've talked about that, mixtures of gases. And so having a high concentration of gases also affects your reaction. So again, we can think back to the Haber-Bosch process, Trying to keep those reactants concentrated, trying to figure out how you drive that ammonia and keep that equilibrium going. And so of course, it also depends on the molarity. And we've kind of gotten a taste of that with just our acid. So 1 molar versus 3 molar HCl. And we probably noticed, that the higher concentrations tend to react faster. And so temperature, of course, also affects the reaction rate. So this, again, kind of goes into our kinetic energy and what that's related to. And so this is just, in general. So every 10 degrees Celsius that you rise in temperature, the speed of the reaction doubles. Again, that's just a very broad general statement, but again, we can think back to our gas chapter, right? If we increase the temperature, our molecules are moving faster and also have more energy. So again, those more productive collisions. So I'll just add that phrase that we're having productive collisions. And again, right, think about that activation energy. So you have to have enough energy to overcome all that. And so again, we'll look at these equations as we go through this chapter. And so then the nature, or right, what state these reactants in also affects the reaction rate. And so this again goes into, right, how do we design reactions? And so just in general, small molecules tend to react faster than large molecules. So thinking of just like, you know, a chemist reacting two things together in like an isolated system versus once you get into more complicated like biological molecules, trying to control those and study those reaction rates can be more challenging. Gases tend to react faster. So if you can bubble in a reagent as a gas, that might be a good way to achieve that reaction. And then of course, liquids react faster than solids. So again, that's always a challenge. So usually, right, in your reaction, the first thing you're concerned about is how do you dissolve your solid or something? Like what do you do to kind of get that in a medium where it's active and they're both floating around and can collide. And so you may also know this, so powdered solids are more reactive than blocks. So of course they have more surface area. And so with that, we can think of an example. So powdered zinc, for example. So powdered zinc, I've never seen it happen, but it does have a flammability hazard. And so, right, you would not want a bunch of zinc to go up in flames, especially the powdered zinc. And then versus solid zinc, right, solid zinc is not going to light up. It does not have a flammable risk. And so a lot of other metal powders are like that. So aluminum powder is the same, where that metal can be flammable, but obviously aluminum solid, right, doesn't have that same effect. And so that goes into the surface area, and so you'll have fun with that today in lab, exploring powdered versus our block reagents. And then obviously, right, certain chemicals are just inherently more reactive. So we talked about, again, our alkali metals, that they're more reactive as they move down the periodic table. So this is, again, something to kind of keep in mind potentially, but also from a safety concern. So also safety. So as they get more reactive, right, that's a good thing in some ways, but then that's also a danger of safety. So you always have to kind of balance that reactivity versus also safety. And then I'll add to this though, because this is also just like a slight oversimplification, because we also would want to look into reduction potentials, which we'll get into later, because this is not always a full story of this potassium versus sodium. And then ions tend to react faster than molecules. So again, if they can go into solution, then they're already free-floating ions to react versus molecules, right? Some bond has to be broken. Oh, any questions on kind of the overview so far? All right, so then we'll start sliding into the math here. And so rate is just our quantity changes in a given period of time. So we could take, right, our rate of speed or travel. So that's just, right, our change in distance over some sort of time. And so we'll be doing again, the same thing of just how do we determine what's our change in reactance rate? So we have a change in distance. So what's our change in reactance over what period of time? So that's what we're going to be looking into. And so now we're starting to get into the math. So we said the rate of our chemical reaction then is measured in terms of how much the concentration of a reactant decreases. So if it's a reactant rate, it's decreasing, and then or the product concentration increases. And again, it all depends. As we get into it, we'll kind of discuss more how this works, but it really depends what species you're able to monitor. So if you're lucky, you can measure both the reactant and the product concentration, but sometimes you may only be able to measure one, and you'll get a much better taste of that next week in lab. And so our general rate can then be expressed as our change in our concentration of, in this case, our reactant, so I2, over whatever time. And then we have our negative sign for our reactant, since again it's decreasing. And so, right, this is just writing this out. So of course, if we have a period, 2 time periods, we can figure out, right, our change in concentration. And so now we can look at this graph here. And so let's look at our reaction. And so let's just start off by rewriting. Oh, we didn't write our reaction. So let's look at our reaction here. So we have H2 and I2, and looks like we're measuring HI. So we have our reaction, right, H2. Oh, they wrote it here. There it is. It's so small, I didn't see it. So this is our equation. So it's balanced. I should write our state. So everything's in our gas state. And then our graph is only measuring our hydrogen concentration and then our product concentration. And so, of course, as time goes on, the rate of the reaction generally slows down because our concentration of reactants decreases. And then at some period, our reaction stops. So generally when our reactants run out, or of course we reach equilibrium. And so now let's look at how we can measure our rate. So we have, right, our average rate versus our instantaneous rate. So our average rate is just our change in measured concentration in a particular time period. And so, right, the larger the time interval, the more the average rate deviates from the instantaneous rate. So does that mean this would be our rate for like our whole reaction time? But then we could also measure, right, our instantaneous rate as well. And so for our instantaneous rate, we can just get the slope at any particular point. So they've kind of done that here. And then we can figure out, right, our change in concentration over time there. And so, of course, if you're in calculus, you know that this is also the same as the first derivative. We won't get, again, too into calculus here or anything, but just nice to appreciate that. And so now they just kind of showed all this. We have, right, our time in 10-second intervals, and then our H2 concentration measured. And then notice, right, they took the change in concentration over these 10-second intervals, and then just compared that rate. So again, just notice right, kind of our decreasing rate as our reactant is consumed. All right, so let's see how we can write our reaction rates. And so we'll continue with this reaction. And so in most reactions, the coefficients of the balance equation are not all the same. So we know that, right? And so in this case, we're in a 1:1:2 ratio. And so that means, right, our rates will be different. So we're saying for every 1 mole of hydrogen used, we'll use 1 mole of iodine, but then 2 moles of HI. And so therefore, right, the rate of change will be different. So in order to make it the same across all of them, we have to multiply by 1 over their coefficient. So here's kind of the generalized form. So note, right, so we have coefficient A with our reactant A plus coefficient B with our reactant B gives us product C balanced by coefficient C and product D balanced by coefficient D. So then let's go ahead. How would we write it out for our equation here? So go ahead and just kind of write that out. So now accounting for their coefficients. So we should have written out, so we have a coefficient of 1 for H2. So our change in hydrogen over time, so still over 1, is equal to our change in iodine over time. So also 1, so that's fine, is equal to our change in concentration of HI over 2 change in time, right? So basically we're saying that our rate of H2 and iodine are changing in half the rate of HI, right, since we're producing twice as much HI.
Do we put negative signs in front of those hydrogen?
Yes, sorry, so those should be, yeah, negative. Since it's just kind of the opposite, right, so it's losing it, so. And so then let's compare. And so we can kind of walk through this then and see that we get the same rate of our reaction. And so I'll pull their numbers because it's hard to kind of tell. But then what they are showing here is, okay, well, let's look at H2 and figure out what the rate is and the instantaneous rate. And we're looking at it right at the same time point. So at 50 seconds, so here we are, they have it noted here. So I'll highlight where we're looking. So we're comparing our rate at 50 seconds. If we use our hydrogen here, so of course it's decreasing, but then we do change in concentration, and they said it was about 0.28 molarity difference over this 40, right? So again, you just take that by finding the slope of the line. So then they made their little slope there. And so then, let me pull up my calculator so we know that we get the same number here. And so, of course, it's decreasing, so it's negative, or I'm just caring about the rate, so we know it's be positive. So 0.28 divided by our 40 seconds gives us a change of 0.007 molarity per second, again, our instantaneous rate. But then we can see that HI gives us that same answer, again, at that time period. So there's our tangent line drawn. And so they said, okay, we're looking at a change in height of 0.56 molarity over 40 seconds. And then don't forget, again, that 2 factor to account for the fact that we're making 2 equivalents of hydroiodic acid. So 0.56 divided by 40, and then divided by 2, though. And so that gives us the same rate there. So that all makes sense. That matches up, so that's good. And so let's kind of at least discuss briefly over how to measure the reaction rate. So we could go on like a huge tangent on how to measure the reaction rate. But basically, right, we don't have to measure all of them. We just need to be able to measure the concentration of at least one of the components of our mixture, right? So we saw that with our rate. And so again, we'll talk about this more. So you guys will get to use your spectrophotometry, right? So your little UV vis spectrophotometer. And so that's a great way of monitoring different species. And so if you're lucky, this is a good way to do this, like in the real world, in research. So some trouble with this is, of course, it's not generally air-free. They do make UV vis machines that, of course, you could put in a glove box and it would be air-free, but you have to be set up for this. And obviously, you also have to have a colored compound, which doesn't always happen. And so you can also do continuous monitoring. So if you're lucky, you can look at it by what's called our proton NMR. So again, this just looks at all the hydrogens in your molecule and kind of gives you a pretty picture. And usually you would know kind of what you're looking for. So you have to kind of know either what the product looks like or the reactant looks like. And it has to be something that you can monitor. And so you can use other, what are called heteronuclei. So people like phosphine ligands, I'll make a better P, since they're NMR active. So this can be a good way to monitor your system. And I'll also throw in there carbon-13 NMR, but this isn't as useful as like the proton, which is fast, and phosphorus is really fast. And then anything else would have to be like your own system. So there's also like nitrogen NMR, but not used a lot. And then you can also do sampling as well. And this could also involve NMR, or sometimes we could also use mass spec. So trying to shoot our reaction mixture through the mass spectrum, it gives us a mass, and then we're kind of comparing our abundance of peaks. So again, it depends what you can measure. And so it mentions the sampling technique, and it says it's stopped by quenching. So usually this just means you remove an aliquot or a small portion. And then there may be what's called like a workup. And so that usually means like maybe you have to turn it into a salt or just kind of clean it up from your reaction mixture. So usually you dissolve it in like ether and water and do what's called an extraction, and then you get your sample. So this I would say is tricky. So this is always kind of the tricky part of research. And right, you have to, again, set up your experiment, make sure that you can actually monitor what you're trying to monitor. And so again, they're mentioning our spectrophotometry, and so other things you could measure pressure. I don't see this too often, at least in the types of literature that I look at, so kind of more organic-y, inorganic. You could look at polarization, so this would tell you how polarized something is, but this is very specific. So you would have to have like a polar molecule and be looking at that, or have that change. So, but spectrophotometry is one that's used a lot. So like I said, you'll get to see that next week in lab and get to do your own rate determine. Oh, pause in case. Any questions about kind of that? And so blah, blah, blah. So this is just more of what we were saying, how you can take a small sample and then again do your analysis of whatever you're trying to do. And then again, right, we have gas chromatography. So this is what I was saying, the mass spec. So they're often called GCMS, which is gas chromatography mass spectrum. And that just means, right, you take your liquid sample and then it shoots it, aerosolizes it, and then again you see all the peaks associated with the mass. All right, so now you know how to measure it. And so now let's again continue with our math. So like we mentioned, our rate law has to be determined experimentally. And personally, I feel pretty good about this, right? Because it means we have to look at data and analyze stuff, so that kind of feels good to me. And again, we'll look at the reaction and how it depends on the concentration, and we'll see which reactants it's dependent upon. And then changing our initial concentration of the reactant should therefore affect your initial rate. And so the rate law of our reaction is our mathematical relationship between our rate of the reaction and our concentrations. So our rate is just defined as this. So rate equals K times our concentration to the N. And so let's just look at that. And so it's raised to the concentration of each, it's raised to the, I screwed that up. So we have to determine the order here. And so the rate law, so we'll talk about what N and M are for our orders, so we haven't gotten there. And then K is our rate constant, which is, again, something we will calculate. Right, so basically recap, we said we'd have our rate, which is just our change in concentration over time, and then we're going to figure out our rate constant. This is our concentration, of course, and then, like I said, we will determine the order. And well, what does that mean by order? And so basically it depends, well, how much does our change in our reactants change the rate? So basically change the order, what's called, for the reaction. And so right now we have our reaction, two equivalents of NO plus one equivalent of oxygen gives us two equivalents of nitrogen dioxide here. And so our rate is given to us by this expression. And so notice, right, it has a little 2 on the NO and 1 with the oxygen. And so that means it's second order with respect to NO and first order with respect to O2. But again, need to determine. So we don't have enough information. We're just accepting what they've told us. So right now, we still haven't looked at data that makes it clear. And then what we can say, though, is we can add up our coefficients, and we get to the reaction as third order overall. So we really haven't explained anything yet, but let's get to it. All right, so now what do we mean by orders? Well, if something is 0 order, and right, so your rate expression, this is just generic, so that would mean your rate law is equal to Ka to the 0. So a to the 0 just gives you K. And so this means that if we're 0 order, then the rate of the reaction does not change dependent upon our concentration. So doubling A has no effect. So, right, you can double it, you can triple it, doesn't matter. Your rate is just your rate. It will be K. And so that's 0 order. And then with our K units here, because then we have to get our appropriate units. So our rate will be molarity per second there. And so then first order means that it's to the power of 1 then. So if it's first order, the rate is directly proportional to the reactant concentration. So if we double A, then that doubles the rate of the reaction, right? And then you could quadruple A, quadruples the rate of the reaction. So times 4A equals times 4 reaction. So then the rate law simplifies to this. So if it's, again, first order, right, that's just equal to our rate constant times A. So again, our concentration does change it. And then our rate constant units K are, K is per second, and our rate, again, is molarity per second. So watch your units on K then. And so then second order, which now you can probably guess what second order means. So now it's proportional to the square of the reactant. So if you double A, you quadruple the rate. So then, right, 3 times A would be 9 times the rate. And so then our rate is just K times our A squared. And so now K has to have units of over molarity over seconds to cancel out this molarity squared to give us back our M over second units for rate. And this will also make more sense as we do kind of practice. So I have a lot of practice problems at the end, so. And so really there aren't too many examples of like third order reactants. So right, you can imagine that could be a thing in theory, but I'm not sure that there are any, so I would have to ask the internet. But we generally don't see third order, so that's why we just have 0, 1, and 2. And so then, okay, well, what do we do now? And so how do we determine the rate law when there are multiple reactants? So this is something that we'll run into. And so we'll have to change the concentration of each reactant and hold the other one constant. So we'll see, again, examples where they do that. And so you have your initial concentration of each one, and then change each one, and then you can, again, determine the effect. And so, again, this will make more sense as we go through the practice problem, but differences in our reaction rates are compared when we only compare the difference in one reactant. And so again, it'll make more sense as we go through this example. All right, so now we're looking at this reaction. So NO2 plus CO gives us NO plus carbon dioxide. And so we have the initial rate of the reaction is measured at several different concentrations of the reactants with the results shown at the right. And so from the data, determine the rate law and the rate constant. So take a few minutes to at least look at it, and then we'll parse through what it's asking. See if you can answer those questions. Kind of what do you notice about the data? So just what are some things that we noticed?
Well, the CO practically doesn't change it at all. It
So-
went up when the molarity went up by 0.1, the rate only went up by 0.0001.
So you looked at 2 and 3, so you saw the concentration doubled, but then the rate either basically didn't change or, so then what do you think? So now we have to figure out our rate law, right? So we have our rate is equal to, right, in general, our NO2, oh, I forgot K. So some K times NO2 to something, and CO. So you guys are telling me CO you think is to the 0 order from no change here? So that's what that's showing, right? So probably no change, because really our answers are, is it first, second, or 0 order? And so since you said it basically didn't change, or going up by 0.001, I'm going to put 0 order for CO. So did everybody follow that? And then what about NO2? What do we think for our order? What could we compare?
I think it's second order because the changes like in 1, 2, and 4, the concentration. Well, I mean, we already determined that it was 0, so it's not technically an equation anyway. But if you wanted to assume that we might get that wrong, you could use 1, 2, and 4, and they all have the same concentration of CO. But when you double the concentration of NO2, it goes up by like a decent amount, and then it goes up by way more when you add in quadruple it.
So that looks good, and I would just divide, you know, if you have trouble seeing. So we're just comparing, so I was just looking at 1 and 2, so just like you said, right, this doubles, but then this seems to go up by 4, right, I get 3.9, but obviously, right, it's real world data, it may not be perfect. And then I like that we could verify, so that's times 4. And let's just double check, so 0.033 divided by 0.0021. And so, yeah, that's about 16, so that works well. So I agree, second order. So now we can rewrite this, so our rate is equal to K, and now it's going to be NO2 to the second, so I just got rid of our CO. All right, so this is at least A. So we wrote out our rate law. And so how do we figure out our rate constant? What information can we use? exactly. So I'll just repeat in case you couldn't hear. So basically pick any data point, right? So this is our rate. This is our concentration. So now we can go ahead and plug in and solve for K. And I just picked the first one because it was there. Again, it doesn't matter which value you pick. So now 0.0021 molarity per second is equal to K times our concentration of NO squared. And so that's 0.1 squared. And so now you guys can help me. Oh, I've already screwed up the math. So did we get K of 0.21? And then don't forget those units are funny of over molarity over seconds, so that, again, our molarity squared cancels out to give us molarity per second in our rate. All right, questions about this one? And so this gives you a pretty good idea of like all the types of problems you'll see. So there'll be lots of data tables that you'll be looking at for this chapter. And so now we'll look at the integrated rate laws. And so again, we're just saying that we have our reaction and we get products. And so we have some rate law that depends on our concentration of A. And so we don't have to worry about the calculus. We'll just give you kind of our rate laws. And I forgot to print out our cheat sheet. So I'll print this out either during our break if I'm fast enough, or might have to wait till Thursday. But let's at least start going through these. And so then we have our zero order reactions. And so if we want to plot them, so notice time versus concentration just gives you a slope, and your slope is equal to negative K. So this could be useful for, lab in the future, especially next week. This gives you an idea of what to do. And then your integrated rate law. So this is useful for solving things. Like I said, I'll give you the cheat sheet, but then you're just kind of figuring out different formulas. And so notice that means we can solve for any point in time, and 0 is, of course, our initial concentration, and then again, depending on what values are given, you can solve. And so this is important, just knowing, again, how to graph it and what gives you a straight line. So again, for zero order, we're plotting concentration versus time. And then half-life, if we had a zero order half-life problem, you can use that equation there. And so then first order, so this is first order, so notice it's now the natural log of A versus time. That gives you the slope, and slope is still equal to negative K. And again, our useful reaction, so again, notice it's our natural log, so we have to take the natural log of that.
Could you go back to the zero order?
Oh, yeah. Still copying? Good. So I'm back to first order. So again, you might want to write this down gonna need to print you the cheat sheet. And then this is also useful, so your y-intercept is your initial A concentration, again, could be useful. So generally, most half-lives are considered first order, so this is a half-life equation you'll generally see, so when we do the half-life problems. People copy that. And are we ready for second order? Still writing. And then, so our last one is our second order reaction. So notice, right, the graph looks different now. So now we plot 1 over A versus time, and then time is still on our x-axis, and now our slope, though, is positive, and slope is equal to K. And so notice our integrated rate law. So it's given as 1 over A is equal to KT plus 1 over our initial concentration. And again, this could be useful information for next week's lab. That might help you. And then half-life, if you had a half-life problem in second order, it'd be 1 over K initial, but usually you don't see these. It's always like a first order half-life. All right, I think this is a good break point. So I think I'm going to run and try to print out this reaction summary for you guys. And I'll also print out, hopefully, because we'll talk briefly about radioactivity. So I'll try to print out this cheat sheet as well. And then, all right, so let's do that. So we'll break. And then we'll either look at some practice problems when we get back, or we'll continue with radioactivity. So probably try to be back by noon, so it gives you like a 10-minute break. I will go print stuff off. I can also leave it here, wherever.
And I kept having to, like, in case it's dashes and not dashes. I've been like, sometimes and there's like, it sounds like it's coming from back, right? But what I thought was like some water bottle thing.
Yeah, there's nobody here. I don't know. I mean, I have to burn it, but again, I just
But it seems loud enough that you notice it, right?
you do the general studies, then you're actually, there's less requirements for the general studies associated with it. So you'll probably earn it anyway, so you might as well. You might have to take like the knowledge class or something. Yeah, and it's just also, we have to treat them as because I wasn't thinking that, and just like, interesting.
Give me the job.
That's not really.
Like almost for nights.
It's just but if you put them over on the other side, I like have a day where I like take off the nail polish, and then I wait until the next day to paint them, because I'm like, that was too much work. It's so fun. Oh, and I think I also make cuticles. That's so gross. I'm done.
That's all that.
Yeah. I found out it's like I don't.
Oh, no, I'm ready, I just don't.
But like if I don't, I don't. So I
I don't know. I might put on like.
I always like, those ones are always like too big or too small.
No, I like it.
Yeah. And it makes me sad because exactly. I get nail on my finger, literally, it's the nail itself from where it grows out, and I'm like, oh my god, I'm so like.
Oh.
I think it's literally because I'm fighting this so I've like trained it to grow that way. So it makes it so mad.
It's a lot of
I
salt.
just have a deep curve because of my fingers.
Yeah. That there really is. First.
I'd say that's more than
Oh, also.
Oh, I-
And I was like, are you just a really?
Not that.
Because the last like 3 classes, it was.
Going to the laughing.
And I was like, I hope my mom partner wants to be here. She missed the final, but I think she was like making it up. She was taking anatomy and she also took biology.
And then you had to go back.
I can't believe you did really good. I am still not. I feel like I was in I don't know. Like there was one question that was like really and I was like, I literally didn't even attend that place because I'd already been here 2 years. But she's like at most everyone was so silly. But I was just like, I just can't do this. I'm like, I'm like, I'm not doing it like if I get any of these right as a fly, like